What the heck is up, guys? It's Jacob here, and in this video we're going to be making a temperature controlled fan controller, if you will, which controls the speed of the fan, or controls when the fan turns on or off, via a temperature sensor. So you can actually use that temperature sensor to put it on a heat sink or in some type of an environment where you want to have this fan actually respond to the temperature change. So today we're going to be doing this using a thermistor. So we're going to build a voltage divider thermistor circuit. It's very simple. But in another video, perhaps we'll look at an actual little TO92 temperature sensor package, and we can do it with that as well. But for this one, we're going to be using a thermistor. So let's get right into it. All right, guys, just real quick, I just want to show you guys how we're going to set this up. So we're going to be using an Arduino Uno for this. You can use just about any Arduino board. They all work. They all have pulse width modulation. They all have analog input. So it doesn't really matter. And so essentially what we have here is just a simple voltage divider network, right? And so I'm using a 10K thermistor. If you don't know how thermistors work, or you don't know anything about thermistors, watch my video on thermistors. This is a negative temperature coefficient device, so an NTC device. Which means when this device heats up, its resistance is going to go down. So this resistance is nominal 10K at I think around 25C. So if it gets hotter than 25C, this resistance is going to start to decrease, and you can see our voltage divider is going to start to increase, okay? And down here I just have a fixed 10K resistor, that's this guy right here, and it goes down to ground. So normally, if these were both 10K, obviously this is going to always be a fixed value, but if this was at 10K, we'd get about 2.5 volts here, right? This is a 5 volts from our Arduino. And so as this device gets hotter, its resistance will go down and its voltage will go up. And the Arduino will read that. And so we don't really need to modify this too much. I mean, you could put a potentiometer here if you wanted to kind of like tune it. But the good thing about using an Arduino is we can really do a lot of that handling. We can process this voltage and do whatever we want with it in the Arduino. We can use it to vary fan speeds linearly. We can set our own kind of like an equation to deal with this. We could also set ranges, so we could say if the temperature is in this range, turn the fan on 25%. If it's in this range, turn it on 50%, 75%, or whatever, you know. Or you could just use it as a simple switch. You could set a threshold and tell it when to turn the fan on or off. There's so many things you could do. There's an unlimited amount of things you can do to control this, and that's really all going to be defined in our software. So we don't, this good thing about using the Arduino is we don't really have to worry too much about fine-tuning this resistor network or anything like that. And just I thought I'd show you guys real quick. This is the formula for this voltage divider network. So V out is the point that's going into it's out of our resistor network and into our microcontroller analog input. So this is going to be A0 in our case. So I'm going to use analog input as 0. And the output voltage is going to be equivalent to R2 over R1 plus R2 times Vn. In our case, Vn is 5 volts. And this is just, without a doubt, you guys have seen this. This is just a voltage divider equation. So just for a simple voltage divider, this is how it works out to be. But you'll notice R1 is on the bottom. So it's inversely proportional to that. So as R1 starts to decrease, our overall voltage, since it's on the bottom, is going to increase. Our output voltage is going to increase. And so that's how we're kind of basing our software. If you have a PTC device, so a positive temperature coefficient, it's not a big deal. You'll just negate everything in software, right? So it's not a huge deal. What else? Or you could just put that on the bottom and it would do the same as well. So you could flip these if you had a PTC device. So the actual Arduino itself is not powerful enough to drive a fan or some device like this for a couple of reasons. For one, notice it's at 12 volts, so this fan is at 12 volts. You might be dealing with a 5 volt fan, a 12 volt fan, a 24 volt fan, doesn't matter. It's not really gonna drive it unless it's a 5 volt fan. And even if it is a 5 volt fan, the current output of an Arduino is like maybe, you know, I don't even know, it's less than 100 milliamps probably. I don't know what, I have to look at the data sheet again for the actual chip, but it's really small. I can guarantee you it's probably less than 100 milliamps, so it can't drive very much at all. And so to handle that, we have to actually integrate it with some type of a transistor. And I really recommend you guys use a MOSFET transistor because they're the simplest to use. You can use a BJT if that's what you guys have lying around. You can use, say, an NPN or a PNP, it doesn't matter. But then you got to worry about your actual gate current, and you got to do a little bit of some extra work there as far as biasing that transistor goes. You got to put some resistor network in there. So we'll talk about that in other videos, but I'd recommend just stick with a MOSFET if you can. So Here's what's going on. This MOSFET allows us to drive a higher current with this Arduino. This Arduino can't really drive a higher current on its own, and it allows us to interface it with a higher voltage. So basically this guy here, this whole thing is the MOSFET. It has this little Zener built in it, so this is a little protection diode, so this is not some external component. And so the gate is driven directly by the Arduino. So the MOSFET itself is a voltage controlled device, so there's really no current flowing through here, so we don't have to worry about a resistor in series between the microcontroller and the MOSFET. It doesn't really matter, so we can drive the gate directly, so that's kind of nice. It simplifies it a little bit. The source goes down to ground. This is an N channel, by the way. This is for an N channel MOSFET. For a P channel, it'll be completely different. You'll also have to negate it in software if you're using a P channel, but and then the drain goes up to the negative terminal of our motor that we're trying to spin, or the fan, right? So the negative terminal of our fan, and then the other side of the fan goes straight up to our plus 12 volt or whatever rail that we're working with, right? So that's how it works. It's pretty simple. And so for this video, I'm going to be using a 2N7000 device, so that's this guy right here. It's only rated for 200 milliamps, so don't bust my balls on this, guys, if you're playing along at home. I know it's not really quite the amount of current that we should be doing. We should have a little bit higher than this because this fan has a 250 milliamp rating on it, so it says it actually draws up to 250 milliamps, but I think we'll be fine for this. You could use something like this, or if you're driving a higher power device, you could use some TO220 package or whatever. It doesn't really matter, as long as it's rated for the voltage and current that you're working with. One thing that is very, very important that I will say you have to look for in your device is the actual gate threshold voltage. So you want to look for the maximum gate threshold voltage. That is saying the maximum voltage it will take to actually turn on the gate of your N-channel MOSFET or P-channel MOSFET or whatever. In the case of this 2N7000, it's about 3 volts. So what that's saying is it will take no more than 3 volts to actually turn on the gate. You don't want to look at the minimum, you want to look at the maximum. And it should be 5 volts or less. If your maximum gate threshold voltage is above 5 volts, there is a chance that this microcontroller won't put out a high enough voltage to actually turn your gate on. Alright guys, so here's my setup. It's wired just like I showed you on that schematic, so it's wired the same, but I just want to draw your guys' attention to a few things here. So here's the Arduino. I haven't hooked it up yet. And so this is our 12 volts coming in, or whatever voltage you're going to be working with for your fan. It's our higher voltage coming in. And what I want you guys to notice is that, first off, the positive lead of our higher voltage supply, in this case our 12 volt supply, doesn't even hit our breadboard. Nothing over here is touching 12 volts at all. So don't even run 12 volts into your breadboard. No need to do that, right? 12 volts goes straight into our fan. So it goes straight into our fan just like the schematic. This circuit really is just switching on and off our ground path to the fan is all it's doing. So you'll notice our ground goes into our breadboard, and I'll show you guys that up more up close here in a minute, and then our output of our N-channel MOSFET goes out to the ground on our fan, to the negative side of our fan. So that's how that's working. So closer up, first things first, I want you guys to realize here that the ground of our Arduino, so the ground on our Arduino is tied to the actual ground on the breadboard, that is tied to the ground on our power supply. So our higher voltage ground and our ground from our Arduino 5 volt supply are tied. They are tied so that we can have the actual current flowing for our signals. It is important that those grounds are tied. Nothing will be damaged from that. Just don't tie your higher voltages to your lower voltages, obviously. That's why our 12 volt doesn't even hit this breadboard. So going into the Arduino, so here's our little voltage divider network over here. So we have 5 volts coming from the Arduino going into the positive rail on this breadboard. This thermistor is getting, one side of it is going into the positive rail. The other side goes to that kind of voltage divider point where those two resistors connect. So that's the point where those two resistors connect. And our fixed 10K is going to the ground. So it's to ground, just like the schematic. The output of our voltage divider network goes through this yellow wire into A0. So A0 is getting the output of our voltage divider network. Whoops. And then our MOSFET, so its source is tied to ground. So the source is tied to ground. So that's where it's getting all of its kind of like power from, if you will. And then the actual gate is going straight from this orange wire into our Arduino. I'm running that on digital pin 3. You can run it on any digital pin you want, just make sure it is a pulse width modulated pin if you want to do pulse width modulation. So we can't do pulse width modulation unless you use a PWM pin. And on a lot of Arduino boards, they either say PWM or they'll have that squiggly line right there next to the actual number that indicates that it's a PWM pin. So you can actually use it for PWM. And then the drain of our little MOSFET here is going out to the negative side of our fan. So that's how this whole guy is wired up. So let's go ahead and hook it up, and I'll show you guys what we need to do in order to get this thing working. Alright guys, so I have the board hooked up here, and we're going to run some code. I'll show you guys that real quick here. But before I do that, I just want to let you guys know that we are actually using a different board now. I'm not using the Uno anymore. I'm using the Arduino Duomenionov, just so you guys don't freak out about that change. My Arduino Uno was giving me some issues. It wasn't wanting to communicate with my computer for some reason, so I used this board instead. It is pretty much identical to the Arduino Uno. All the pinouts and everything are exactly the same. There's really no difference. I think just the serial communication chip is different, but besides that, it'll operate exactly like an Uno, so there's really no change there. I just wanted to let you guys know that. Alright guys, so I'm just going to show you what code we're running here. This is not the actual final code, but this is a process that we need to do in order to kind of get an idea of where our sensor or our voltage divider is going to sit in the range that we're going to be operating in. So right now, let me show you guys the code real quick first. So here's the sensor pin. I just kind of did all of our declarations, so our pin declarations. So our sensor pin is on analog 0. PWM, that's our output going to our transistor. This is on pin 3. So this was from our voltage divider network. And I just made this value called sensor val. We'll see that in a minute. I didn't actually initialize it, but I just kind of declared it there. And then in our setup, really easy, all we have is our pin modes. So I said the sensor pin, that is our voltage divider, is an input, so it's going into the analog input, obviously. And then pin mode PWM output, so that is our PWM pin driving our fan. It is an output. And so the purpose of this serial begin here is we're going to actually look at the 10-bit value coming from our voltage divider network, from our actual thermistor sensor, and I'll show you guys why that matters here in a minute. You guys will see pretty fast. But so in our loop, here's what's going on. We have that value that I declared before, that sensor value. I'm going to say the sensor value, this is our 10-bit value, is equal to the analog read of our sensor pin. So all this is doing is reading the voltage on our sensor pin, and it's putting it into a 10-bit digital value that we can read. And then what it's going to do is it's going to take that serial .print line, and it's going to print out that sensor value. And I put a delay here for 1,000 milliseconds, so every second it will update this. And what it's going to do is it's just going to read the actual value coming out of our voltage divider network, put it into a 10-bit value, and it's going to print that on our screen here, and we'll see those actual values coming on our screen. And this is really important to find the lower limit of our sensor and the upper limit, depending on what you're going to be operating the sensor in. Alright guys, so I'm going to go ahead and open up the serial monitor right here, and what this is going to be printing out is our actual 10-bit value from our voltage divider network. So this is kind of, if you will, the temperature of our sensor. Obviously it's not the temperature, but showing us right now, because my sensor is just sitting there on the breadboard, it is the lower limit, or what I would expect to be kind of the ambient room temperature right now of this sensor. So this is what the sensor would be putting out, what our voltage divider would be putting out at this ambient temperature. And we'll actually get to see this. So I'm going to write this value down right now, 431. And so if the room was a little bit cooler, if our temperature was a little bit cooler, it'd be a little bit lower than this. So let's just say it's going to start out at like 400 actually, to keep it simple. And what I'm going to do is I'm going to heat up my sensor, and I want to see kind of that maximum value. I want to see the upper limit of our sensor, or where I want my fan to go to 100%. So what temperature I would want my fan to go to 100% at. So what I'm going to do is I'm actually going to take my soldering iron, and I'm just going to place it on the sensor, and you guys will see these actual values start to go up. Alright guys, so I have my iron here, and I'm going to touch it on the sensor, so you can see it's jumping up, and I only have it updating once per second. I don't need it to update 10 times a second. You can, by changing that delay value, update it faster, but really I just kind of want to see where it peaks out at, because I'm going to use this value as my 100% for my fan curve. And you guys can really set your fan curves however you want. So I'm seeing it's kind of starting to slow down here. And I'm going to go ahead and say, we'll just say 800 is my maximum value. So at 800, I want my fan to be at 100%. So my lower value is going to be 400, and my upper value is going to be 800. And so, like I said, that's really going to depend on your guys' application. You guys might not want your product to get as hot. You might want your fans to kick in at a higher temperature. And you guys can take these values, you can use them to adjust your PWM linearly. You can use it with if statements to set kind of conditions. So if it's in a certain range of temperature, you can pulse width modulate your fan output to a certain amount. So you could say it's 25%, 50%, 75%, or 100%. Or you can just use a threshold limit. Alright guys, and so here's the rest of the code, and I will post this down below the video, like I said, there's many different ways of approaching this. This might not be the best for your case, so definitely it's going to depend on your application, but I just want you guys to realize that I added another actual integer up here, and I called it PWM val, and this is going to be the actual value that we write out to our pulse width modulation pin. So it's important to understand that our sensor val, when it actually reads the analog voltage of our voltage divider, it's going to convert that to a 10-bit number. So it's going to be anywhere from 0 to 1023. And it's going to output our pulse width modulation value at an 8-bit number, and that's going to be anywhere from 0 to 255. So what I do is I say I'm going to use the map function, and this is going to be very linear, so this is going to behave very linearly. So I'll explain what that means. So PWM val, this is going to be our output value, and what I'm doing is I'm mapping the sensor value, and what this means is I'm going to kind of take our bottom limit of our sensor value, which I said was 400. So this is going to be equivalent to 0 on our output. So this, if our sensor value read 400, our pulse width modulation val, or PWM val, would be 0, and that would actually write nothing out to the fan, right? And if it went up to as high as 800, 800 is our maximum value, so it's going to map that to 255, and it's basically going to try and map this as linear as it can. So it's going to take this 400, make it our lower value, it's going to output that as a 0, and it's going to take our 800, make that our upper value, and output that as 255, and that's 100% pulse width modulation, or pretty much just straight 12 volts. And it's going to take these values and it's going to assign them to PWM val. So it's going to be basically looking at our sensor values and mapping them on a range from 0 to 255 and outputting that to our PWM val. And then all I'm doing is I'm doing an analog write down here, and I'm writing our PWM output pin to our fan. That's the actual pin 3, and I'm writing it PWM val, and PWM val is just that value that we just talked about. So that is the actual value of the pulse width modulation for the fan. And so there are some issues with this. For one, the fan takes quite a bit of current when it first kicks on. So you might be pulse width modulating your fan as much as 25%, and it'll put power into the fan, but the fan might not actually start spinning yet. So what I would recommend is we might add some other code here, which when the fan first kicks on, it runs the fan at 100% for say a second, and then it goes down to the pulse width modulation value. Because if you don't do that and the fan starts off at, let's just say 0, and then you start feeding pulse width modulation into it, it might not actually start spinning until you get to 30-40%, because sometimes those fans take a large amount of current to just start up. So we'll do that by applying let's just say 100% value for some amount of time, and I'll show you guys that in the end. But I just want to show you guys this simple code running here on the actual circuit. So let's go ahead and take a look at this. Okay guys, so here is the setup, and it's pretty much ready to go. Everything's good to go. I'm just going to turn on the power supply, and so you can kind of hear it. Actually, you can hear that ringing noise, and that is that pulse width modulation. As you can see, the fan is not spinning yet. You might have seen it try to turn on, but it's not actually spinning yet, and that's because what I just explained earlier, these fans take quite a bit of power to start up. If we actually gave the fan a little bit of a push, it would, at this point it's barely going enough, but sometimes it'll have just enough to actually get itself going. And that's why when we turn the fan on, I want to add a little bit of code to where when this fan first turns on, we'll run it at 100% for, say, a second, and then we'll go into our pulse width modulation. Also, I don't think it's really worth pulse width modulating these guys probably below 10%, because it's not going to have enough power to actually maintain the fan spin. So we'll probably map it to go from, say, 10% duty cycle up to 100%, rather than from 0% to 100%. But we'll start tuning that in a little bit. I just want to show you guys the very basic operation so you can kind of hear it going. And I'm going to take the soldering iron and I'm going to touch this sensor. There it goes. You can hear that frequency, not the frequency, but the pulse width modulation changing, starting to speed up. And it's going to go pretty quick because we're heating the sensor up quite fast. And so there is another issue with this that I didn't really explain, but if we go over our map value, so if we hit 100%, this is actually going to go, and it's going to go, if we go past 100%, so if we go over 800 on this sensor, essentially, our map is going to start at the very beginning, and it's going to go to 0% again. So you'll see that here, it's slowing down. Our sensor is actually above 800 right now, and it's going to cool off, and then it's going to kick in again, and it's going to come in at 100% right there. So that is, again, a flaw with our code. So I'm going to rewrite the code, and I'll show you guys a little bit of an updated version with some of these problems worked out. Alright guys, so I just want to show you a few of the fixes I made to those problems, and I will post this code down below. Again, you guys can tweak these values to meet whatever kind of criteria you need for your project, or however you want the fan to behave. You can get really advanced with this, as advanced as you want, but this is just very basic. So let's take a look at it. So before, we had the problem with our value. If it went over 800, it would basically loop around again, and we'd start at our lower value of our duty cycle. So I capped that off. So basically, here's what's going on. We're reading the sensor value, and I'm saying if the sensor value is greater than 800, let's go ahead and bump it back down to 800. So that's going to say the sensor value will never reach higher than 800. If it does, we're just going to push it back down to 800 anyways. This is our older serial monitor code. We don't really need this for the actual program to operate anymore. It doesn't really matter, but I'll just leave it there. The actual PWM values, this is that mapping function that we did before. So basically, I'm actually going from a range from 450 up to 800 now. So I bumped our range up. And so if it's below 450, if our actual sensor value is below 450, what I'm going to do is I'm going to actually make our PWM value 0. So this turns the fan off. So it's in an off state. And basically, once we hit 450, I want to start the fan at a 10% duty cycle. That's what 26 is. It's about a 10% duty cycle. That way that fan has enough power to actually turn on. And it goes pretty slow at 10%, so that's good enough. And then 800 is still our top range, and that's going to go to 255 or 100% duty cycle. So this map function works perfect now, and it won't actually overflow and loop around again. So that's what these limits do. And if we're below 450, like I said, we just turn the fan off. The PWM value is 0, which writes a 0% duty cycle to the fan. And in the very end, we still have our analog write, where we write the PWM value to the actual PWM pin for our fan. So let's go ahead and take a look at this new code in operation. Alright guys, so let's go ahead and see this code in operation. So it's on now, the power supply is on, and our sensor value is below that 450 volt threshold. So our fan is currently off. And if I take the soldering iron, I'll touch it a little bit, and you'll see it kicks in at that 10% duty cycle, which is enough to actually start the fan. So let's go ahead and do that. Kicks in right there, barely enough to start the fan. So we might have to start at a higher percent duty cycle, and it starts to ramp up there. You can hear it speeding up. Still going. You can hear that ringing. And there it goes. So you cannot hear the ringing anymore, so that means it's not really pulse width modulating, and it's at 100% duty cycle. So the fan is all the way on, or it's at 100% duty cycle. And so that is the upper limit. That's the 800 or higher limit on our sensor. And so as I take the iron off, it will start to cool off, and we'll watch it kind of slow down. This is in real time, so it might take a minute. You can hear it. There comes that PWM. Maybe if I put my finger on it, I'll absorb some of the heat off the sensor. It'll slow down a little bit faster. Now we'll just let it cool off from the ambient air temperature. And you can see it starting to slow. I don't know if you guys can see that really well in the video, but it is slowing down quite significantly. Perhaps I could actually use the fan to cool the sensor off. And so it's really coming to a good slow now. There it goes. And we're going to hit that 450 volt limit, or the 450 value limit of our threshold, where the fan will actually kick out and turn off. So it's really slow now. So you might really not want to start out at 10%. You might want to start out at say 25%, but there it is. So there's that limit where it kicks off. All right guys, so that pretty much wraps it up for this one. I will post that code down below for you guys to look at, and you guys can kind of modify it to meet your own needs, however you guys need it. It'll depend on really what kind of a fan you're working with and what your project really needs, but you can get as wild and crazy with that as you want. It doesn't really matter. So I hope you guys enjoyed this one. Definitely give it a like if you did, and subscribe for more content like this. I hope to see you guys in the next one, and as always guys, have a good one.